It is generally acceptable to have 2 meter stacks mounted on a single property, provided certain conditions are met according to the National Electrical Code, specifically Section 230.2 Cone. These conditions typically include: firstly, the stacks are mounted on a common support structure. Secondly, the distance between the stacks should be adequate, often a minimum of 3 feet is specified. Thirdly, each stack must serve a separate building or sub-building. Given that Building B is a separate structure, it is necessary to supply a grounding electrode system at that building and connect it to the ground bus in each subhill within Building B. This requirement is outlined in NEC Section 250.32b, which mandates that grounding be provided for all electrical systems and circuits of each building or structure. This grounding ensures a safe path for fault currents, minimizing the risk of electrical shock and equipment damage. There are several key aspects to consider when implementing a grounding system for a separate structure like Building B. The grounding electrode system must be designed and installed in accordance with NEC Section 250.50, which specifies the requirements for grounding electrode systems. This system typically involves 1 or more grounding electrodes such as ground rods, ground rings, or concrete encased electrodes. The selection of the appropriate grounding electrode depends on factors such as soil resistivity and local code requirements. It is important to ensure that the grounding electrode system has a low impedance path to ground. This minimizes the voltage rise during a fault condition and helps to quickly clear the fault. The grounding electrode conductor, which connects the grounding electrode to the ground bus in the subpanel, must be sized appropriately based on the size of the ungrounded conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor. The connection between the grounding electrode conductor and the grounding electrode must be made using approved methods such as exothermic welding or listed connectors. These connections should be protected from corrosion and mechanical damage. The ground bus in each subpanel serves as the central point for connecting all equipment grounding conductors and the grounding electrode conductor. The ground bus must be securely bonded to the metal enclosure of the subpanel. Equipment grounding conductors from all circuits in the subpanel must be connected to the ground bus. These conductors provide a path for fault currents to return to the source, tripping the overcurrent protective device and energizing the circuit. The size of the equipment grounding conductors must be based on the size of the overcurrent protective device protecting the circuit. The NEC provides tables that specify the minimum size of the equipment grounding conductors. In addition to the grounding electrode system, it is also important to ensure that all metal enclosures and equipment are properly bonded. Bonding is the process of connecting metal parts together to create a low impedance path for fault currents. Bonding helps to minimize voltage differences between metal parts, reducing the risk of electrical shock. Bonding conductors must be sized appropriately and connected using approved methods. Particular attention should be paid to bonding metal water pipes, gas pipes, and other metallic systems that may be present in the building. These systems can provide a path for fault currents to enter the building from outside, so it is important to ensure that they are properly bonded to the grounding system. When installing meter stacks, it is crucial to ensure that they are properly labeled and identified. This helps to prevent confusion and ensures that each meter stack serves the intended building or sub-building. The wiring from the meter stack to Building B must be properly protected and routed according to code. This wiring should be installed in conduit or other approved raceway to protect it from physical damage. The size of the conductors must be based on the load requirements of Building B. Overcurrent protection must be provided at the meter stack to protect the conductors from overload and short-circuit conditions. The overcurrent protective devices must be sized appropriately based on the ampacity of the conductors. It is also important to consider the voltage drop in the conductors from the meter stack to Building B. Voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC provides guidelines for calculating voltage drop and specifies the maximum allowable voltage drop. It may be necessary to increase the size of the conductors to minimize voltage drop. In summary, when dealing with separate structures on a single property, it is essential to adhere to the NEC requirements for grounding and bonding. A properly designed and installed grounding system will ensure the safety of personnel and equipment and will minimize the risk of electrical hazards. Firstly, make sure the meter stacks are mounted on a common support structure. Secondly, confirm that the distance between the stacks is adequate, often a minimum of 3 feet. Thirdly, verify each stack serves a separate building or sub-building. Furthermore, supply a grounding electrode system at Building B and connect it to the ground bus in each sub-panel within Building B. Additionally, design and install the grounding electrode system in accordance with NEC Section 250.50. Also, ensure all metal enclosures and equipment are properly bonded. Lastly, properly label and identify the meter stacks and protect the wiring from the meter stack to Building B, routing it according to code. All of these steps help to ensure the safety and functionality of the electrical systems in both buildings.